Hello there. My name is Nick Fitzke, and I'm a professor in the Department of Chemistry at Mississippi State University. You are currently watching the third in a three-part series on processing and inspecting simple NMR spectra in a Linux environment using programs like NMR Pipe, Sparky, and Pokey. If you haven't watched the first two videos, I encourage you to find them in the link below, along with the simple data files and the scripts that we'll be using in this video. In this final video, we look briefly at opening files in Sparky before moving on to Sparky's successor, which is called Pokey. We focus on opening the spectrum, looking at how the spectrum is displayed, and performing a basic assignments transfer. As with the other videos, here are the obligatory disclaimers. First, this video is tailored to the environment that we have here at MSU, and it may not match what you have. I think that's probably less of an issue with Sparky and Pokey, but there might be some differences, so watch out for them. Second, remember to always follow the instructions of your advisor or PI. They may want you to perform data visualization or assignments slightly differently than I do. Finally, remember that this video was recorded as a discussion between me and a new graduate student in my lab. My apologies if the production quality isn't the best. Now that we're done with all that, here's the last video. I hope you enjoy it, and if you do, please consider subscribing. Okay, in the last video we looked at how you could process things in NMR Pipe, and again the big advantage of NMR Pipe, just to keep our eyes on the main thing, is that you get this very nice documented list of all of the processing stuff that you've done. Whereas that you can dig that out from Topspin, but this is very clear, and it's also lends itself very well to scripting and if you've got 1,000 spectra to process, you can set this up as a script, and they're all processed exactly the same way. And prior to that, we looked at how you copy the data over in the first video, and actually talked about the NMR spectrum themselves. So this video we're going to focus on the two programs that we mainly use in the lab, and we'll stick mostly with the second. But the first program that we'll often use to look at NMR spectrum is called Sparky, and Sparky was developed at UCSF many years ago, but Woong-hee Lee at NMRFAM took it over when he was there. And so you just start it by typing Sparky. And we'll see that there's a lot of similarities between this program and the second program that we'll use, which is Pokey. And they're both, Pokey was developed from scratch by Woong-hee, and he eventually left NMRFAM and took a faculty position at University of Colorado, and so he's now doing his own thing. But we occasionally will still use both, although I think most of the group will eventually migrate to Pokey because it's newer. The first thing it will ask you, because of the way that I have it set up, not every time will it do this, it'll say, hey, do you want to create the Sparky or Pokey folders? And generally I like to keep them local. So if I have a whole bunch of files pertaining to, let's just close that. If I have a whole bunch of files pertaining to GB3 variants, what I might do is, again, this is my main directory, and then my spectra are stored here, and so I'll often start Sparky from this directory, in which case now I'll say yes. And what it'll do, again, I forgot to type ampersand, but this is a good reminder. So you just type Control-Z and then BG, and now Sparky's running in the background. And now you'll see that it created three separate directories. Lists, which is generally where NMR assignment peak lists are saved. Projects, which is where project files are saved, and save, which is where your spectra save files are stored. And so from within Sparky, now I have these options in here, and I can go File, Open, and I can navigate. Now it starts me in the save directory, and it can open Sparky and Sparky save files, but it can also open UCSF spectra files. And so if I go to where I process my data, and I select the test.ucsf, and it doesn't, we name it test because it's convenient, and that's a Frank Delaglio thing too, but it doesn't have to be, it can be any UCSF file. But if I click on that and hit open, I'm going to get a very nice spectrum, right? And again, Sparky and Pokey do not do any kind of processing, but they're mainly for NMR spectrum visualization and analysis. So you can do assignments in Sparky and Pokey too. I find that's a little bit easier to do in programs like Kara. But if you're looking at peaks and you're just trying to say what's happening to these peaks, Sparky and Pokey are the ones you want to do. But since they don't have any processing ability, you have to do that in NMR pipe first. Right? So and we can see the spectrum looks very similar to what we were just looking at in NMR pipe, right? It's GB3, it's the variant, and notice that if I click on this window, I will, all of the options here have 2-character codes by them, and these are called accelerators, right? So for example, if I want to zoom in, I can click down here and I can do zoom in, but I can also click into my window and type lowercase z, lowercase I, that's zi, okay, I got it here. Yeah, so you can see I'm typing zi and I'm zooming in, I'm zooming out, and it's usually much more convenient to type those 2-character accelerator codes than to mess around with the Windows options. Again, we're not going to focus on Sparky here because I think it's better to look at Pokey. But one thing to note here is if I save the spectrum, so think, how does this system sort of handle files, right? So again, it never overwrites the binary files that you've processed, right? Again, Sparky and Pokey are there to do analysis. And so it's actually really important from a scientific integrity point of view that none of the spectra that you're editing are changed, right? You can annotate spectrum, you can change the color, you can zoom in, but you never want to change the raw data. And so because of that, these programs both have a save file that's affiliated with the actual UCFS or UCSF spectrum, and that file stores the things like their peak lists here. You've zoomed in. You're showing. It says the contour levels that you're dealing with. The color of the spectrum. Even like the position of the window on the screen. It'll save information like that. But it never changes the spectrum. All that's saved in a separate file called a .save file. And this is just a text file. You can take a look at it if you want. But it just has all those parameters saved in there. And so if I save this as test.save, that's not going to be super useful. But if I change it to K19G HSQC, maybe put a little underscore in there, now it's clear what this spectrum is. And I can put every single, like if I have 20 variants of GB3 here, I can put all of them in this same save folder. And it's very easy. Even though they might all be called test.ucsf in this directory, they can be called something different here. And so I'll save that. And then that will save if I go here to my save directory. So if I look here, then there's the save file I just created. And again, if I look here, it's just a text file. And all the different options are stored in there. Now, often you'll have multiple spectrum open at once, and that's a really good advantage for what these programs let you do. And so if you look here at File Save, there's not only just a save and save as. This corresponds to the selected spectrum. Notice the selected spectrum always has the top, and it's listed as selected. But I can also do project save and save as. And so a project is a collection of save files, right? And so again, if I have 4 or 5 different spectra open, each with their own .save file, A project says, okay, these spectra have a relationship, and I'm going to open them all together at once. And so if I do, let's do GB3 variance dot proj, and it's going to, but it's going to save that project file, but then it's immediately going to save all my spectra file as well. So I can hit OK and don't ask again. And if I look here in my window, it says saving the .save file and then saving the .proj file. And now this is a stupid case because I just have the one. I just have the one spectrum, right? But if I start Sparky up again, and now I hit open, I can open the individual spectrum, so I can hit file save, and notice it makes a backup file. So you don't have to like just save it as a .save, that's fine. But I can either open the .save file, I can go all the way back and open the .ucsf, and that'll forget all of the contouring and anything else I might have done. But I can also open, up here, I can open the projects file. And here, if I had 4 or 5 spectra open the last time, it would bring them all open. And so that's a really convenient way to do that. And again, if I close this, now there's all sorts of ways you can change things. And so if I type lowercase s, lowercase t, you know, it might not be good to call this test, even though it's saved as K19G HSQC. Maybe I want to actually name that window K19G HSQC. And now if I hit apply, this is a little bit easier to manage than a whole bunch of files that are test. Again, think about what makes your life easy. But now if I go into here and I do project save, again, it saves the UCSF file, or saves the .save file, but it also saves the project. And if I go QT, it quits everything. But now, so that's Sparky, and Sparky and Pokey have a lot of overlap, right? A lot of the accelerators are the same, a lot of the workflow is the same, but Pokey is starting to incorporate a lot new features. And so if I'm in the same point and I hit Pokey, pokey.sh, that's how you do it. And so notice it does the same thing. Now here it's going to ask me, do you want to create a Pokey directory that'll store all of your lists, projects, save? What I personally prefer to do is put list, projects, and save close to the data. Some people prefer to have a massive Pokey repository of all of the files in their system, all of this .save files, all of the .proj files, and that way it's all in one place. I don't like that, but some people do it, and if you really want to do it, you can do it too. I think there are really big advantages to storing a separate list, project, save directory for each project that you're working on, because it will make it much easier. And so I'm going to hit no. And so again, it looks similar. This is a much more graphical view. You have different mouse options, and again, Pokey has a lot of its own videos, so we're not going to go into everything. This is basically just to get you started. But here again, notice there's still accelerators, and they're still, look to be very similar to what you had in Sparky, and that's because they were, developed primarily by the same guy in the last few years. And so we can again go to Open Project, and guess what? They're compatible, right? So if I hit, maybe they're not compatible. This is probably a file system thing. Because it looks like it's not. So it looks like it's not reading that file correctly. So let's try to look at open. Oh, and it's writing. So it's looking here. That's probably part of it. So I've got to go to my notebook here. Save. Now if I click this, and so again now, so it is compatible from the save point of view. I guess if I hit File, Save As a Project, and overwrite it, and that will replace. Okay. So, but notice again, if I'm in here and I type JS, again, it's giving me the same things that, you know, now it's also, let's do File, Save As. That's new. It might just be in a weird space looking for folders. Again, I think when I've tried this down on your lab laptops, everything has worked. But so I think the first thing to sort of think about here is how would you get peaks, right? So this is great. This is a nice spectrum. It's beautiful, but I don't know what the peaks are. And so here again, there's lots of ways for you to go learn Pokey, and I think we're going to, you know, Woongi's already doing tutorials on things, and he's probably the better source for that anyway. But in this case, if we've got a variant of GB3, and in this case this is the K19G variant, we're going to go and we want to be able to so now here I'm not finding it, and again the windows, the menus are a little bit different, but I know the accelerator is RP for read peaks, so I'm going to type RP, and in this case I can go and then browse to find the old copy of the wild type GB3 peak list. And so if I click here and then hit create peaks, you can see it's created those peaks. Now it's hard to see because it's not, you're not seeing a whole lot here. But if I go and type OZ for ornament size, there we go. And I can make these a little bit bigger. So the ornament sizes are in W1 ppm. So the W1 axis is here, W2 axis is your proton. And so if I want my label size to be bigger, I can make this maybe 0.6 ppm. Hit apply. So now you can see the ornaments much bigger. That might be a little bit too big, so let's do 0.4. And then I can make the ornaments themselves, so the peak ornaments, the little boxes, I can make those, you know, maybe 0.15, so double the size of those. And again, I'm not changing anything on the spectrum here. I'm only changing how Sparky is rendering this, or Pokey is rendering the spectrum. And so now from here, I can look in, and from my point of view, and we'll just get these assigned because I think it's probably good. What I typically like to do is inspect all of the peaks, right? Because you can see, even though these are mostly the same, coming from the wild type GB3 to this K19G variant, I like to make sure that they're all centered and they're all good. One thing that students will commonly do is they'll just select all of the peaks, so PA for select all, and then PC, which centers everything. But you often will, because you're not looking at individual peaks, you often make mistakes in over-centering your peaks. And so you might have a peak that you know is actually two peaks, and it'll just cause those to collapse onto one. Right? So what I typically like to do, I type EU to undo, edit undo. What I typically like to do is I scroll through my spectrum, and I use like a snake approach. Right? So I find the rightmost peaks on my spectrum, and I start here, and I go into my peak selection mode. So this is what this peak here means. And now if I drag over peaks, it's going to select them. And those are clearly well-resolved peaks. I'm going to center them, PC. So from there, what I would do is I would snake up and just continue looking for peaks that I need to deal with. And so thinking along this lines, I will, there's obviously no peaks that I've touched here. And so now I'm going to look at my x-axis, and so I'm right around 7.6, and I'm right around 9.6. So maybe I'll do a little bit of overlap, and I'll scroll to the right so that 9.7 is the leftmost peak. And so now, okay, this looks okay. I'll hit PC, center that peak, and now I scroll down. All right, and so I'm scrolling down, and you can jump through this a lot. And again, for most of these, it's very simple. If I had just selected every single peak and centered them all, I probably would have gotten 98% of them correct. But on the other hand, for some of the more crowded areas, maybe I'm not going to get them correct. Or maybe by over-centering, I'm making an approximation that's not really valid. And so, for these, I'm probably just going to keep doing it. But notice if I do PC, again, Y3 jumps to what's ostensibly a local maximum here, but it's probably not this Y3 peak here. And A20 is now centered on one of these sync artifacts. And so, easy enough to fix. I can drag that up here, and again, just type PC, and it'll center all those selected peaks. And I can drag this one, if I click off and then drag this one close, and then select that peak and do PC. Now it'll be the same. This brings up the idea on how to change the contour levels. So again, from within view, you can adjust these, and many of the contours options are the same as they are in Sparky. But at this point, I type lowercase v, lowercase c, and so from here, or uppercase C, lowercase v, capital C, from here I can adjust the lowest and the lowest negative contours and the lowest positive contours if I don't want to see those sync artifacts. All right, so this is one way to do it. You can also use the very old Sparky approach where you drag up at the top of the contour list to increase the number of positive contours. You can drag down to increase and decrease the negative limit. And if you drag in the middle, you increase the total number of contours. So I can go from low contours to high number of contours. And then dragging all the way down here, I can adjust the total floor of my high and low peaks. Oftentimes for quantitative work, what I like to do is type CT, so lowercase c, lowercase t, and I like to find reasonable values that I can use for both positive and negative spectra, or negative contours. So if I do, for example, 3 times 10 to the 6th as my lowest, use 14, 1.25, those are fine. And then minus 3 times 10 to the 6th. And 14, 1 point. That way I can ensure that I'm looking at the same upper and the same lower contours, and I'm not fooling myself by totally eliminating the negative contours while only viewing the positive contours. And so finding a value here that you like and then sticking with it, this lets you have a little bit more control over the contour limit. And I like to usually have the same positive and the same negative contours, unless there's a really good scientific reason not to. Another feature that you can do here, notice that these labels are kind of overlapped. You can always type LU, and that will move your labels so that they're separate and they shouldn't overlap anymore. But now continuing on my snake, I'm moving down, snaking through the spectrum. And at this point, again, I'm just selecting the peaks and centering. All of these, P, C is an option so that you can see here center peak. You can go in here and hit select all, right? So PA is P lowercase a. It might be nice to have like a select visible, but I don't think there is one of those right now. But anyway, so it doesn't take long to snake through the spectrum though. So again, I'm already here at the bottom. I'm going to start at 8.7 ppm, so I'm going to move this so that 8.7 is now on left-hand side. And notice that for whatever reason this has two E56s. We can get rid of that. And we'll select this, lowercase p, lowercase c. Again, starting from 8.7 and now snaking it back up. And again, I'm missing some peaks here at the side, but that's why I don't, I'm not going to go to 7.6. My next step will be 7.7. So there'll be an overlap area where I can hit more peaks if I need to. But here again, looking here, so this is Q. Moving things to where they're sort of close, and now I can select it. Now notice there's nothing here for K19N, and this is because it's we're dealing with a K19 variant. So this doesn't have a lysine 19 or even asparagine 19. This has a glycine 19, and so I know that I'm going to expect an extra peak up at the very top of the spectrum where there's an extra glycine. And so I'm going to select this peak, and I'm going to delete it. And I'll just keep scrolling up. And so these peaks, these are all okay. All right, and if I do LU, I can, notice that all of those peaks are pretty well centered. Notice here, though, right? So these are the cases where we haven't collected enough spectral resolution to resolve E27 and T25. And so if I just went in and blindly selected those two and did PC, it's going to collapse them to the same peak, and that would be bad. So that's why we're doing this. We're going through and we're going to, I'm going to assume that E27 is still the upfield peak, T25 is still the downfield peak, and 35 and 15 are the same here. All right, and so, but now I'm not going to automatically center those. Those are going to be, my best estimate of where those peaks are. Right, now, Sparky provides some additional options. So if I select all four of those peaks, and then instead of typing PC, I type PI, it's going to do an integration. So it's actually going to try to fit these peaks to a particular line width and say, well, if I know there's two peaks here and two peaks here, can I come up with some line widths and some positions that are consistent with what I'm dealing with? Sometimes you need to do that if you're trying to get really quantitative results. But for this, we don't, and so I'm just going to leave them pretty much like they are. That's plenty good for what I'm dealing with. Okay, and so now we're starting to see additional peaks coming in here. So these are, these are unassigned because they represent asparagine side chains. We'll look at those in a bit. And if we go up and we continue selecting peaks, right? So we're just snaking through some more. And so again, now I'm going to bring 7.7 to the left-hand side of my screen. And now we're snaking down. And so some of these peaks are actually, you can see that they're a little wide, so you're actually starting to resolve the HN-H alpha coupling. So that's why this peak looks a little bit wider than this peak here. Do LU. So again, the N37 is a wider peak in the proton dimension than the D22. If we type lowercase v capital S, I can look at the slices, and you can see it's really clear that the N37 peak in the proton dimension, I don't think I can, I can't easily move my mouse away, but that's shorter and fatter than the D22 peak in the proton dimension. And the difference is the HN-H alpha coupling. So in the N37 case, we're starting to resolve that. The coupling is rather large. And the D22 case, the coupling is small. And that coupling can actually be related to secondary structure. Notice this one is also kind of short and squat. So we're seeing the HN-H alpha coupling. not fully resolved, but starting to be resolved. So just sort of talking through the spectrum as we go through it, but mainly focusing on continuing to center peaks and get things positioned nicely. So again, lowercase c, lowercase p, lowercase c. And so now we'll just, probably we don't have that much, so we'll just move all the way to the right. Yeah, so the spectrum ends at 6. And there's no more new assigned peaks here to center. So now I'm basically, and I can go hit V, capital S, and that turns off those slices. And if I type lowercase z, lowercase f, you can see I have my full spectrum back, right? And all the peaks are aligned. In this case, all of the ornaments are nice and visible. Further centering the peaks doesn't do anything. And we're in a pretty good spot. Now the question becomes, what happened to our glycine 19? Right? Well, I told you that glycine was going to appear up at the top of the spectrum. And you notice that there's not really a whole lot of other peaks that are assigned here or unassigned. Right? Now looking at it, I think this is going to be your glycine peak right here. But how would I know that? What's my rationale for thinking about that? Well, I'll tell you there's two things I'm thinking about. So first of all, I mentioned that these peaks are asparagine peaks, NH2s. You don't see every asparagine in a protein generally because they're often surface exposed and the hydrogen exchange on those NHs is occasionally pretty fast, so you often don't see them. But when you're getting ones that make hydrogen bonds or that are somewhat stable or close to acidic residues, the local pH is low, or you have peaks that are or your whole spectrum is at low pH. You're going to see more of these NH2s. You can also get rid of them depending on some of the delays in your pulse program. Yeah, not going to get into that, but for example, on our TROSIs that we collect here, you rarely see these peaks because they're filtered out from the TROSI, or they're much weaker. But if I look here, notice it's an NH2, right? So it's two protons that have the same nitrogen attached, attached nitrogen atom. And so if I look at these two, there's a pair, right? And they even have sort of the same shape because of the spectrum collection, right? So this one and this peak line up to a horizontal value almost perfectly. And I can press F11 to do zoom mode. And let's zoom in on this region, actually. Let's zoom in here. So if I look here at the center of this peak and the center of this peak, they're practically the same. That's strong evidence for the fact that these two protons are attached to the same nitrogen. And that means that they're probably from the same NH2 side chain, right? And importantly, look over here, right? The center of this peak is not quite the same as the center of this peak, right? It's a little bit more upfield, but these two also align perfectly. And similarly, if I go here, right, those two align perfectly, those two align perfectly, and these two align perfectly. And so that's one way I can tell, oh, well, that's coming from an amino acid backbone, whereas this is coming from a side chain, asparagine or glutamine. Right? And so you get this information just by looking at the chemical shifts. And so that's why none of these peaks are assigned, because we don't have the side chain assignments in here. But that's also how I can know with a pretty good degree of confidence that even though this isn't exactly up the same level with my other glycines, this is almost certainly going to be that glycine 19. And so it's not, I haven't proven that yet. I would need to do some experiments to demonstrate that, but I'm probably 90% certain that this is the new glycine. And so what I can do is I can hit F8. That brings me into peak addition mode, and I notice that my mouse cursor changed over here. Maybe if I hold it over here, there'll be a tooltip eventually. Yeah, find add peak. And so if I select this, it now adds a single peak corresponding to that. And now if I type AT, it brings up the assignment window. And from here, I can type K, or I guess G19N, G19HN for the amide nitrogen and amide proton corresponding to what I think residue 19 is in this protein. And again, go back to my peak selection mode. I can drag that. I could also have typed LU. And now I have a reasonably good approximation, again type lowercase z, lowercase f, of all of the assigned peaks in this spectrum that we can then go and now look at analysis and see what's happening with these resonances for this very simple but very useful protein. And so I think that's pretty much where we can wrap it up. This covered loading a spectrum in Pokey, dealing with contours, dealing with basic assignments. That kind of stuff is going to come up over and over and over again. And so, this tutorial will hopefully help you walk through. One final thing just to sort of put us back where we started. If I type lowercase l, lowercase t, and hit update, it brings in all of the assignments. And now I can save those assignments. And it'll end up being in my list directory, or it should end up being in my list directory. And so if I hit save, now I have a text file that I can read into other spectra. And then if I save my project, this is a configuration issue that I have to deal with. But let's make sure that I hit File, Save As. Yeah. So I have to go in and type, or put the directory in. On your computers upstairs, you shouldn't have to do this. And if it continues to be a problem, we can talk to Woonghee and see if he can fix it. But I'll call this gb3variants.pokey.proj. And now, since it's in a directory that I can actually edit, we should be okay. So if I do JS, now it's stopped giving me an error message. You can see it's saved K19G, GB3 variants, Pokey. And if I close this, and then close, I can hit quit because I've already saved the project. And so now if I do pokey.sh projects GB3 variants proj, Pokey, Pokey, nope. And so now it brings up everything. Now again, I saved the peak list, and that's a text file that some other user can then use, or we could share with collaborators or whatever. But all of the peak position or the peak assignment information is saved in the .save file. So you don't have to save the peak list every single time. That was just an example to show you how you might do that if you wanted to import it into another spectrum later on. But this pretty much wraps up what we need to cover, and it covers a lot of the basic functionality that we would normally do with Pokey. And so if you've watched all three of these videos and you're in my group, thank you for following instructions. If you're not in my group, thank you for interest, and hopefully it helps you get started in using these NMR assignment and analysis tools in a Linux environment.